I'm today's host, Juling Shih from National Central University, Taiwan. It's my best honor to introduce our speaker today, Dr. Chang, William Sayer Chair in Material Electrochemistry, Department of Chemical Engineering in UCLA. Professor Chang's research focused on the synthesis and chemical processing of novel materials, atomistic understanding of solid-state interfaces, and their applications in microelectronics, optoelectronics, solar cells, batteries, and other energy-related applications. Specifically, her research focuses on developing novel atomic layer controlled thermal, radical, and plasma enhanced deposition technique to synthesize compositionally controlled conforming coating, either on a planar surface such as a wide band gap semiconductor, or selectively over complex 3D surface topology such as in a 3D micro battery or fuel cells. She is American Institute of Chemical Engineers Fellow in 2021 and has won Samuel School of Engineering University Service Award in the same year. She has been AVS Fellows and has AVS Plasma Prize in recent years. Her academic achievement is a long list, and I can just name a few. Now, Professor Khan is going to take us onto a fantastic voyage, chemical processing of function-accelerated nanomaterials at the atomic scale. Without further ado, let's welcome Professor Chang to talk about her research and works. Professor Chang.
Thank you very much for the very kind introduction. Good morning, everyone. I think this is early morning in the time of Taiwan, and Happy New Year. I appreciate that you're taking the Saturday morning to join today's lecture. I was told that this particular series is aiming at the primary audience being high school students or early college students. So I hope you will take this opportunity to ask questions, and if there's any part that is not clear, please let me know. I do try to minimize the use of specialty terms, and when I do need to use them, I will explain them. So today I'm going to focus on a fantastic voyage, and this particular topic is really looking at how we can use chemical processes to enable us to basically make miniaturized devices at the nano scale. And we will focus today's talk on function-accelerated nanomaterials. And before I start, I will just emphasize that this is certainly not my one person's work, right? I have worked with a large number of talented students and postdocs and many collaborators, and I will acknowledge them at the end of today's talk. So I will start with explaining what do I mean by the fantastic voyage and how I describe them over the years. The first time this term is used is actually in a movie in 1966. I did not know about this movie at the time because I was not yet born. But this is a sci-fi movie that talks about a fantastic journey of 4 individuals, actually 5 individuals in this particular case. And exactly what the story is, it will become clear in about a minute or two. While I did not know about that movie, I do know about a story, a children's book in 2010. This is a book that I read with my children. And this particular book is one of many in the book series of the Magic School Bus. I don't know if some of you have seen this particular book series. It talks about this science teacher takes his class on this Magic School Bus onto many adventures. How is that relevant to the research that I do? About 10 years ago, National Science Foundation established the Engineering Research Center at UCLA. This particular research center has a grand vision that focuses on the construction of such a similar vehicle. In this particular case, we wanted to design a unit that has a motor that can drive this particular vehicle. In this particular vehicle, in order for it to be useful, it would have a antenna that can receive and transmit information so that we can communicate with this particular device. And it will also have a memory that allows the information to be stored as the information being acquired. So based on this particular slide, I would like to pose a question to the audience. Based on your observation, what is common in these images that span almost 60 years? I think the chat function may be a little bit difficult for people to use, but I am hoping that you can see that the background in these three images are very similar. In fact, they are all of the blood vessel. And in all the images, the designer very carefully illustrated the presence of a red blood cell. And this essentially tells us that the vehicle that we're looking at here are on the order of a red blood cell, and they are traveling down the human blood vessel. The question is, if we really wanted to make such a vehicle, how should we be doing it? So in order to take a fantastic voyage, how can we make that possible? Clearly, we need to build such a vehicle, right? Let's look at the vehicles that humans have fabricated. Large vehicles such as the space shuttle, vehicles that we probably use on a daily basis, whether it's a bus or a car. In your view, even if you might not have built one, what type of tools are needed to build these vehicles? Okay, so the general type of tools, yes, you probably need some motorized handheld tools. You probably need some drills. You probably need some hammer. You probably need some screwdrivers, and the typical type of tools that you can find. I can tell you today, no one has built a vehicle that is on the order of a red blood cell. But people have made components that would eventually be able to be used in realizing such a goal. So on the image that I show on the right-hand side are some mechanical parts that could potentially be used. They are still fairly large, tens to hundreds of micrometers in size. If we were to further reduce the dimension of these devices, if we were to push them really down to the nanoscale, in your view, what tools might be needed? And this is where we're going to launch a poll where you just need to make a selection. Okay, I see some answers coming in indicating C. Indeed, drills and welders are probably not going to be possible unless we make a drill and a welder that is at a nanoscale. 3D printer is pushing the limit. Large nanometer scale devices people can probably do. Small nanometer scale devices people cannot do. We don't have magic, so it won't be the magic. So yes, this will lead to the emphasis of today's talk, targeted chemical reactions. So what tools are needed at the nanoscale based on what we have looked at so far? The tool should be of the same or smaller size than the device that you're building, right? And we probably need more than one tool. You might have heard the saying, if you only have a hammer, all the problems look like nails. Right? Certainly we cannot solve all the problems by a hammer. So if we want to make a nanoscale vehicle, we would have to have tools that are at the nanoscale. If we wanted to make a device at the atomic scale, then we need the tools of the size of an atom. So this is where we go to the chemistry. In the chemical solutions that I show here, there are many, many molecules in these solutions. You probably have seen or have done experiments in the lab using the test tubes, the beakers. So you know what I mean when I say we use chemistry to enable reactions on surfaces. But for most of the chemical reactions that you can do in a chemistry lab, one thing is common. If you use solution, you put the target material into your solution, the reaction is isotropic, meaning it's in all directions. These reactions do not know the direction, they are homogeneous, and then you're going to see the reaction happening in all directions. If we wanted to build a vehicle similar to the image that we saw on the previous slide, we know they have very, very specific geometry, dimension, and shape. If all the reaction happens at the same time in all direction at the same rate, you will not be able to do that, right? So yes, we wanted to go to the chemistry, but we wanted to be able to control the direction of the reaction. So we have to do something special. In addition, if we are making very, very small scale of devices, I want you to think about the experiments that you might have seen using the capillary tube, right? You know there's surface tension effect. If you have very, very small scale of structure and you immerse that into a solution, you're going to see this surface tension effect everywhere. They might not be able to go into a structure. If you put in a surfactant to let them wet the structure, you get the liquid into the structure, you couldn't get them out because of the surface tension. So ideally, while we use the chemistry to target reaction on surfaces, we also wanted to do this in the gas phase, and we wanted to do it with a control of the reaction direction. Okay, this is when we turn to plasma. For those of you who might not be familiar with plasma, let me just explain this by saying that plasma can be considered as the fourth state of matter. We are very familiar with the three states of matter, right? If you take an ice cube, you heat it up, we have water, liquid state. If you heat it up further, you have the steam. That's the water vapor, as in the gas phase. And we know water boils at 100 degrees C. Now, if you increase the temperature to 10 or 15,000 degree Kelvin, this is when you start ripping the electron from the atom or molecules of your gaseous state species to create a partially ionized gas mixture. And this mixture, we call it a plasma. This sounds like something you might not have seen, but you actually have seen, right? In nature, most of the lights that we can see in the sky actually comes from a plasma. And some of these images are visible to our naked eye. Some of these images shown here are taken by the Hubble telescope. And yes, the entire galaxy is filled with plasma, the stars. We have built large plasma devices. For example, this particular unit I'm showing here is the ITER, International Thermonuclear Experimental Reactor. And this is for a plasma fusion experiment that is planned to run its first experiment in 2025. This date might be changed slightly due to the pandemic, but this is where some of the very large scale reactor has been made by people. These are shown in here to the scale of a person. We have also made very small microplasma jet systems, and some of these have medical applications. They can be used to treat wound, and some of these have been tested to treat aerosol that lands on surfaces during the pandemic. So they are used for medical applications. What we are interested in for making nanoscale structures using plasma can be illustrated by this diagram here. If we have a reactor that is under vacuum, we can feed the gas that is reactive into the system, such as the chlorine shown here. And the plasma is created by typically in an electric or magnetic field, accelerating the electrons, initiating the ionization or dissociation reaction so that you can produce ions, positive ions, and reactive radicals. And these ions and electrons basically make up that partially ionized gas mixture. Because electrons moves much faster than anything else, because the electron has very, very small mass, they are going to reach the surface, build up a potential, repel the incoming electrons, accelerating the incoming positive ions until they reach equal flux. And this provides an intrinsic electric field towards the surface. This particular field is very important because it allows the positive ions to be accelerated almost 90-degree normal to the surface. So most of the chemical reactions are isotropic. They don't know the directions. But when you have ionic species that can be accelerated and the direction can be controlled by an electric field, we now can manipulate the direction of the reactions and control it in a particular way so that we can create these nanoscale structures that has very straight sidewall structures, allow us to pack many of these structures together for many different applications. So the ions provides the reactive chemistry, the energy with the directionality, and the slight change in angles can also help us tailor the structure that we're going to form. The radicals that are produced in the plasma are extremely reactive, so they are chemically active, and their reactivity, while it's isotropic, can be greatly enhanced in the direction where we see simultaneous ion bombardment. This synergistic effect is very important, allowing the plasma to create materials on surfaces or selectively remove material from surfaces. So if we were to use these plasma-based processes to do thin film deposition, laying down materials, or thin film etch, which is to remove materials after a photolithography process, we can build complex structures such as a transistor. This particular transistor structure is a building block of all of our information technology today. Let me show you how this metal oxide semiconductor field effect transistor work. Under normal circumstances, if you do not apply the voltage to the gate, which is the metal orange structure here, no matter what you do, when you pull the increase the voltage on the drain, which is shown in blue here, you're not going to see any current. If you put a potential, a voltage on the metal gate, you're going to induce a channel layer that connects the green area, the source and drain. And now if you try to pull the current, you will see the current flowing from left to right. This represents a transistor on and transistor off state. This binary state is what is needed to do all the binary operation. So you remember our computer thinks differently than how we think, right? For the computer, it's only 0 and 1, the on or off state of the device that operates this binary motion. And in this particular case, one transistor cannot do very much, but 1 million of them, 1 billion of them will be able to do a lot more. So all the cloud computing that we are doing, the telemedicine, this Google Meet meeting that we're running right now are all based on this particular infrastructure. So we are in a very exciting era. This is an era where we measure things by trillions. So since 2020, the number of transistors in chips in logic devices has surpassed trillion. In the smart sensor technology area, they need trillions of sensors in order to realize smart home, smart city operations. So if you are going to make trillions of these devices, you will want to make each one of them really, really small so they don't add up to be a huge size and weight. And the only way that we can really do this is to basically process materials and create these structures that we need using atomic layer processes. And some of this has already been used in the fabrication of the integrated circuits. TSMC, Taijidian, is one that is well known in the world for such advances. If we're making a single transistor to operate that binary code, today we want the device to be at atomic scale. We want to make them smaller because they're usually faster, and we have to address some of the reliability issues. To make them better, we need novel materials, and we need to be able to place them precisely where we want them. Making one transistor is challenging to perfect it. What about to make 1 trillion transistors? The challenge is much greater, right? Not only you need to make one, you need to make many, and they need to communicate with one another. So integration is a very important issue. How we can create these structures reliably so that they can function precisely is very, very important. And nanoscale patterning is really important. Over a large area, we wanted to create many of these tiny little devices at the nanometer scale. We need to do it very precisely, and then we rely on plasma-based patterning process to drive the directionality of the reaction. So today I'm going to touch upon both material synthesis and material patterning. In material synthesis, I'm going to talk about how we can use plasma processing to control the composition, conformality, and how we can use that to create multi-layers and combining material with complementary properties to create new functionality. In the area of material patterning, we're going to talk about how we control the chemistry and the directionality of these reactions so that we can be very specific, very selective, and create highly anisotropic structures. Anisotropic structure is the opposite of isotropic. So this means not in all directions, but in one direction. So plasma-based processes are critical in realizing these device integration challenges. Okay, so now I have gone over the Fantastic Voyage. I've talked about how this is important. I'm going to use 2 examples. I'm going to try to skip the technical portion and try to make this much more easy to understand. So first I wanted to say, if we use the fabrication of the transistor as a guide towards the vehicle that we eventually wanted to make, let's look at which elements in the periodic table has been used over the years. In the last 60 years or so, literally every element in the periodic table has been used. Not all of them has been processed at the atomic scale, but they will eventually all be processed at this particular level. We can design new materials to enable nanoelectronics, spintronics, optoelectronics, photovoltaics, or energy storage devices. And typically, the more element that we introduced, we create the complexity in the structure, we can derive more novel properties. Today, I have only time to discuss one particular material, that is multiferoid material. I will come back to clarify this term first, but I will say the multiferoid material is one that will allow us to make future generations of electromagnetic devices. We can make the memory devices much more energy efficient, so you won't drain your battery as fast. We can make the antenna much smaller. If you ever open up your iPhone, the largest 2 components in your phone, one is the antenna, the other is the battery. If we can make them smaller, we can make them more capable. And we can make the electromagnetic motor at a small scale much powerful because we can minimize the loss. If we can integrate these 3 components together, the vision of our ERC center is to create such a vehicle that can be functional. Today, I only have time to basically talk about probably some specific work that we did on antenna. If you If you have ever driven by those towers that transmit signals for your cell phone, you wonder why they need such a big tower, right? So the antenna size scales with the wavelengths of the information that you are transmitting. So how do we reduce the size of the antenna if the wavelengths of the signal is that large? We will have to convert it, and the process of converting it involves this multiferoid material. Before I discuss the multiferoid material, I wanted to briefly go over the voltage control of magnetism. This is a phenomenon that we have known for hundreds of years. If you pass a current through a wire, you create a magnetic field around it, right? This particular concept can be scaled to make very tiny little wires and create a magnetic field. But at very small scale, a conductive wire becomes very resistive. So most of the energy that you put in is lost to heat. So it's not an energy efficient process. We cannot really use it very effectively. If we wanted to switch magnetization, the best way to do it is to use a designer material where we can put a potential on it. It's a potential. There's no current flowing. By this potential, you can switch the magnetization. It will be a very energy efficient and low loss process. The only problem is nature does not give us materials that can really respond between these two states. If we wanted to use the electric field to control the switch of magnetization, it doesn't happen. Multiferroics refers to multiple, many ferroic order. You might have heard about ferroelectric material where the electric dipole can be switched by an electric field. Ferromagnetic material where the magnetism can be switched by a magnetic field. Multiferroics means a material that has multiple ferroic responses. We simply do not have a material in nature that can allow us to directly control the switch of the magnetization by an electric field. But nature gave us a lot of piezoelectric material and magnetostrictive material. So if we cannot get from this place to this place in one straight line, we can take a detour, right? We use the coupling from the electrical to mechanical change, which is a stress or strain, and then transfer that strain into a material that has magnetostriction so that the magnetization can be switched. This particular process required us to design materials, literally with multi-layers that bring different property together through close interface coupling to enable this strain transfer. If we can do this, we can reduce the wavelengths of the received electromagnetic wave by several order of magnitude smaller. Then we can make the antenna much smaller than what we have today. So how do we design these materials? One way to do so is to look at how we can use atomic layer deposition process to enable the synthesis of some of these materials. Many of them are metal oxides. So if you take a surface that is saturated with hydroxyl group, with these OH groups, you bring the metal that you are interested in through a organometallic precursor. So it's a metal with bulky ligands that helps them to become a gas molecule. The reaction between these molecules on the surfaces are specific. They will only react with the hydroxyl group. Once the surface functional groups are consumed, the reaction will self-terminate. So this is the self-limiting nature of the atomic layer deposition. So once you react all the surface functional groups away, you can introduce a secondary chemical which repopulate the surface with the hydroxyl group. And you have a surface that you can come back to the starting point, and you can repeat this process and build up these multi-layers with the same material or with different materials to increase the complexity of the material characteristics. If we try to do this in a thermal setting, and if I tell you the material of interest includes some of these complex metal oxides, and we wanted to layer them, you can see how complicated it might be, we have to design the molecule that we can bring them onto the surface. And then each of the material in terms of the temperature where we can grow the material well may be at different settings. To quickly ramp this temperature up and down in a vacuum environment is nearly impossible. So we wanted to use the plasma because we're generating these atomic oxygen species in the system that can very quickly react with organic ligands, and that allowed us to grow these complex oxides at very low temperature. I don't intend for you to read this slide. This is just to show you that using this plasma enhanced AOD process, we have synthesized many materials and allowed us to basically create more complex structures. We can control their composition really well. And we can use the conformal characteristics of this particular process to make 2D multilayers, 1D, 3D nanopillar structures. We can even take a mesoporous material and uniformly coat each of the pores with a secondary material to create this 0D, 3D complex multiferoid network. And we have done that. And in this particular case, the conformality allowed us to control the thickness of the coating and how uniform it would be. And that dictates how well we can transfer the strain so that we can flex this porous material for the intended application. In the 2D configuration, we were able to basically take dissimilar materials. You can see that if we want a material that is soft, magnetostrictive, in nature, most of the materials will have certain characteristics, but not the other. We do not have any of the materials where all 4 fields are shown in green, meaning they are all desirable. But if we create these multi-layers, we can actually engineer a material that meets the goal in all of the specification that we need for the intended application. So this multi-layer design is very important to allow us to increase the functionality of the material so that we could integrate them for further application. If we can design the material, and remember when we put them down, they are uniform across large area, they are continuous. I cannot create trillions of devices. I cannot create a vehicle that has different specific structures, right? So I would have to do nanoscale patterning. I have to be able to cut them into tiny little pieces with very, very well-defined structures. And the way that we do it is by plasma etching. So the strategy for atomic layer etching include the following 3. We can use only plasma, where we generate radicals to modify the surface, and we bring in ions to sputter remove the modified material. We can introduce this particular process multiple times. The structure will be reasonably directional, but you can see that there's a little bit of the undercutting using this particular approach. If we don't use plasma, thermal-based process in the gas phase will give you an isotropic reaction. So you will see a hemispherical type of reaction front. You can remove the material, you can continue the process, you can create a dome-shaped structure. It's not going to be vertical. There may be certain areas where you want this type of structure to be formed, but if you want them to be directional, this will not deliver. If we combine thermal and plasma processes, we can use plasma to do the modification and then use the reactive neutral to remove the material. In this particular case, because the plasma defines the direction of the reaction, the neutral species has a very different reactivity between the modified material and the underlying material. So you can remove the material and create an extremely directional structure. So all of this gives you different degree of flexibility in terms of what you're looking for. And to design the chemistry that will allow us to pattern the material well, we typically will use some of the first principle calculations to help us identify the potential reaction pathway. In this particular case, I'm going to use nickel, which is one of the components in these multiferoid material systems. If we wanted to study the reaction pathway, we look at different surfaces, we look at different coordination number centering around the nickel that we're interested in. We look at the potential reaction product that we can form, and then we basically calculate the energy of the reactions to see if this particular process might happen. And this type of first principle calculations can help us determine what might be the driving force to enable these nanoscale patterning. In this particular case, it was clear that in order for this particular reaction to happen, you have to have oxygen species incorporated to the sublayer of the nickel. And you cannot really do that with the reactive neutrals because they don't have that type of reactivity. If you use the ions from the plasma, that directionality can allow you to break through some of the surface layers, and you can introduce the oxygen to the sublayer. Once you start forming these sublayer oxygen, you start removing the material by forming nickel formate as a product when we use the formic acid as the chemistry. And this, based on the results that we're showing here, you can see nickel with different surfaces, with different coordination number, has very different reactivity. So these type of reactions are very specific to the local chemical environment. And we can design the chemistry to make this particular process highly selective. So in this particular case, we use the oxygen to create a nickel oxide layer. The chemical reactivity between nickel and nickel oxide are very different. So the selectivity is larger than 100, meaning that nickel oxide can be removed very easily, but nickel will not. So if I can define the direction of oxidation, I will be able to remove the nickel in only one direction. And the result of that is we can pattern these structures with very well-controlled vertical sidewalls. The image on the bottom are elemental mapping showing all the different elements in this particular complex structure, confirming that we indeed achieved this very directional patterning of nickel. And what is most useful about this particular process is we can apply it to beyond the current IC manufacturing. For example, we have been using this to create structures for the extreme UV photolithography photomask. And one of the most critical component there is an absorber, and we can pattern this to be very fine in structure to allow this technology to be possible. And we can take a structure that is non-ideal, we can trim it and create these very directional processes. So there are many ways where we can use these atomic layer etch process to create nanoscale structures. Okay, so this is a summary of what I would like to emphasize today. By using the plasma where we have energetic ions that we can control the directionality, we can enable material synthesis by atomic layer deposition or nanoscale patterning by atomic layer etch. For deposition, the important aspects are composition, conformality, and our ability to synthesize multi-layer that we can combine complementary material property. For atomic layer etch, we need for the reaction to be specific, selective, and realize the highly anisotropic structure. And if you're interested in this talk, I would like to point out that there is another related lecture that was given by Professor Soo-Jae Kim, where she was talking about the semiconductor technology, but really more on the Tri-Gate device that she invented. And I also wanted to point you to this newsletter. This was published earlier this month as the IEEE celebrated the 75-year anniversary of the transistor. It's a very interesting read if you're interested. So I will end the talk by saying, we have our periodic table. That's our building block. How we put them together, you be the designer. Through atomic layer processing, in the near future, we will be able to realize such a device that can have profound impact in human health and medicine. And how is this related to your study if you are a high school student? I asked the organizers to send me a current high school curriculum from Taiwan. I think this is what you are currently studying, right? You're taking language classes, science, and humanities subjects. For language, clearly you're taking Chinese English, but I would say in the 21st century, programming is a language. It's just like having a second language. You need to be able to speak to your AI at some point. If those of you who follow the ChatGPT, you want to know how they do this, you need to have the ability to do the programming. For the science, any of these subjects are great. For humanities, any of these subjects are great. The intersection between science and humanities is going to become a lot more important in the future. So I will leave you with a poem by Robert Frost. I hope you have read it, but if not, it's a very nice read. The purpose of this poem is not to say you have to choose the road not taken. The purpose of the poem is to say that you have choices. So when you are faced with choices, I hope you choose what you enjoy and enjoy what you do and make a difference to better this world. Thank you very much. I would end with acknowledging my students, collaborators, and funding sources, and I'll be glad to take questions.
Thank you, Professor Chang, for explaining profound theories in simple language, at the same time to give our young audience constructive advices in further study. And I'm also very happy that Professor Chang likes the same poem that I like, the two roads diverge in the woods, and I took the one less traveled by. So that has made all the difference. So now I'd like to open the floor for questions and discussions. Our audience can use the raise hand function to talk to our speaker today, or write down your question in the chat box in either English or Chinese, and we try to relay your question to Professor Chang. Not only we have high school students today, we also have some experts online. And if we have more in-depth or any questions, please, right now, you can interact with Professor Chang.
Well, maybe let me start this question.
Thank you.
That is, Professor Chang, do you know anyone in Taiwan is doing things like this?
In academia, I think Jerry Su at National Taiwan University is certainly working in this area. In industry, TSMC has many field experts in this area because this is what they do.
So you think that so it's possible the first machine would be produced in Taiwan?
Oh, you mean the vehicle?
Yeah.
I am not sure. As you can see, the notion of designing the components to enable that particular vehicle was supported by NSF Engineering Research Center. It's a 10-year effort, right? And it is not at this point with any potential immediate commercial application. So I don't think there is, other than the consortium that we have at UCLA, I don't think there's any other one that is focusing on this. But there are many parallel studies that people are doing, working on small robotics, right? And they may not be a smart device. It may be material that can respond to a stress and can change shape. So those efforts are there. I saw your question was more related to who is working on plasma-based processes. There are many people who are doing that, but aiming at making a miniaturized vehicle that is biocompatible and can be used in the human bloodstream. I think our ERC Center is the only one that is doing that.
Yeah, and maybe I could also follow up, because you just mentioned that your effort, your research is supported by NSF, which is a long-term effort, 10 years or more. So what would be your advice to our because we have something like similar to NSF, we call it National Science and Technology Council, 国科会. What would be your advice to the administrators there, how they should fund the basic research like what you're doing? Because they tend to be very short term. You 2 or 3 years you have to finish your project and get your results. And you think this is the right approach, or you have other advice to them?
I think for anything that is transformative will require at least a few decades, right? So you look at even for something as simple as lithium-ion battery, right? There was 30 years of research prior to that technology become viable, that everyone has that in their phone, and now we have electric vehicle, right? So definitely longer term. The importance of the long-term research, I think in recent years, the most important one is probably the vaccine that we all use for COVID, right? That is also a very long-term application. We didn't know this virus would be this devastating, and we have to borrow the technology that has been in development, right? So yes, definitely, I think 10 years is a long enough time that if an idea really isn't going to work, you will know. But if an idea really is taking shape, you will follow up with additional support. And for most of the breakthrough technology, there's typically 20 to 30 years of basic research prior to that.
Yeah, I mean, almost just a lifetime of a researcher. I think you should come back to Taiwan to tell our big people in the science and technology that they should be patient. But I saw
we try to tell everyone here as well.
As well. Okay. And Professor Shih, back to you. I think there's some questions to Professor Chang.
Yes, there in the chat box there are 2 questions, one in Chinese, and maybe I'll do some translations. It says the thermal activity has great impact and maybe random. How do you reduce the hyperthermia activities and its impact?
Do you mean phonon?
Guanrong, please, are you able to explain it further, your question? Thermal motion of atoms.
Yes, so that's phonon. Okay, so you will see in this work that I presented, right? Everything is at room temperature. So at room temperature, yes, of course, phonon is always there, but it's not something that is the most pronounced, right? So at 40 degree Kelvin, we can study phonon behavior really, really well. And that will make a huge difference if you can control the phonon. Most of the devices, if you think about the vehicle that needs to be transported in human body, it needs to be at the temperature of the human body temperature, right? So it will not be at very low temperature. In the solid state physics field, there's a lot of unique phenomena that people can only probe at very low temperature, because we suppress the phonon so we can then study some of these phenomena, right? So at this particular point, I would say most of the materials, when we operate them at room temperature, the phonon or thermal motion of the atoms isn't something that we are particularly concerned about. It's a very minor component.
And we have another question from our audience in the chat box. She said, can you give some examples that high school students can do to learn how plasma works?
Okay, so if this is related to an actual experiment, you need a pump, you need a tiny little tube that you can cap off, and you need to pour vacuum. This tube ideally will be glass, because then you can see the color of the plasma. For high school, I would suggest that you use, of course, inert gas, right? So you can use air, which is a mixture of nitrogen and oxygen. You need a device to allow you to basically create either electric field or magnetic field. And so do this with care. Don't do this unsupervised, especially if you're playing with electricity. Everything needs to be properly grounded. But if you have a coil around a quartz tube, you can actually create a plasma. Nitrogen plasma is pink, oxygen plasma is blue. So if you have an air plasma, it's probably going to be purplish, right? So that is something that you can do. And then you can start changing, for example, the power, the pressure, you can see the color change. That means the density of the plasma is changing. This is not something that I think that this is not something that I would encourage a student to do at home without supervision. I think you need to do it in a laboratory where there is supervision, especially related to electricity, making sure that everything is properly grounded. There's no, they are a couple commercial entities that sells compact plasma sources, but the cost is not low. I don't know if that would be adequate for a high school student or high school to do, but conceptually, yes, a quartz tube with a metal coil that is properly grounded and then can excite the electric field, you will be able to break down the gas and create a plasma. But if you are not referring to hands-on work, there are many videos that people have created, right, to show you how you can create a plasma. There are some data collection even that you can work with that particular module. So remote learning options are there. If you are interested in those sources, you can contact me. I'll be happy to send you some of that information.
Actually, there comes to a point, how to teach plasma physics in high school. I mean, I don't know how's that being done in America, because in high school there are so many things to be taught to learn in physics. You know, even quantum mechanics is not well covered. I think that they may be given a chapter or so, and but quantum mechanics is very important. And the same as you said, you know, plasma physics, this is a very new concept. It's a bit plasma physics, something between classical and modern physics. You know, it's a new invention. So how can that be included into the modern day high school curriculum?
So I can tell you that it is not in the high school curriculum. I actually recently worked with a group that developed a electromagnetic course for the high school students in the state of California. But I would say the plasma physics course, unless you are a physics student in college, I would say most of the students don't even take that in college. I personally took plasma physics when I was in graduate school. I think in high school, what is most important is the foundation. So if the student learn the electromagnetic theory well, then when they learn plasma physics at a later time, it will not be very hard. But if they're trying to learn this and then realize that they have a fundamental gap that they need to go back and fill, that could be challenging. So I would say, while this is to me, this is a very interesting, exciting technology, I don't necessarily think that high school students should rush to learn this, right? I think if the student learn electromagnetism well, in high school, that is already a very, very important part towards their future preparation in this area.
Unfortunately, our students, they don't learn the electromagnetism very well, you know, because it's been taught in the last semester of the high school, and there's a time they already finished their their exam, and so they don't want to study anymore. So that our high school students are in college are always very good in mechanics, but not very good in electromagnetism.
This is the reality in the US as well. For senior students, especially those who apply for early admission, by the first quarter, they already know where they go, right? And they lost the incentive to continue. And then electromagnetism builds on some of the math that they need, right, in calculus. So they're typically taught after they have the math foundation. So that's why it's always towards the end of the high school senior year. So again, going back to building the foundation, right? We cannot rush to teach physics if the student didn't have the math. And so this is part of the reason why for some students, they feel that college freshman year, maybe a little bit of a review of some of the harder courses that they have in senior year. And that is by design. We need to remind them what they know, right? And then continue to teach them something new. But I think still having that course in high school, if they have seen it once, it will make it easier for them in college.
Yeah, it's sometimes very discouraging for the students. They got A in mechanics, in the first semester, and they got C and D, in mathematics theory, and they just got crushed.
That I understand. Yes, these are harder courses. I sympathize with that. I see there's a question about if the plasma ball is a good equipment to start. I think that is a fun experiment to do, but it is not something that you can easily teach, right? So for example, when we teach, we wanted to give them concrete examples. If we can describe it with a few equations, that is the preferred way, especially if they're taking the introductory course. And so I am all for exposure, right? If they have, if the plasma ball has that wow factor and get people interested, so they're willing to sit through a plasma physics course, great. But I think that is more on the fun aspects, right? It's not something that we can really sit down and go through with them and say, this is how you can create this or control this particular phenomenon.
Okay. I think there are still a lot to talk about, since this is a very professional field and a new field and new discoveries. We hope we can have more time to explore more on this topic. Due to time constraint, we shall end today's session, and I hope we can soon have another talk with Professor Chang. Before we meet again, please stay safe, happy, and healthy. Thank you again, Professor Chang, for sharing with us today.
Thank you.